another example of a graph. F of x equal 2x squared minus 7x plus 9. So that we can take the derivative. We can use the quotient rule here. It's going to be the denominator squared. And then it's denominator times the derivative of the numerator. So the derivative of the numerator is be 4x minus 7 minus the numerator, which is 2x squared minus 7x plus 9 times the derivative of the denominator. The derivative of the denominator is just 1. So then if we distribute we have x times 4x, x times negative 7, negative 3 times 4x, negative 3 times negative 7. It's the FOIL method. I have 4x squared. Outer product is negative 7x, inner product negative 12x. It gives us minus 19x. Negative times 3 times negative 7 is plus 21. Distribute the minus sign here. We have minus 2x squared plus 7x minus 9 all over x minus 3 quantity squared. So we can combine like terms. X squared, 4x squared minus 2x squared will give us 2x squared. Negative 19 plus 19x plus 7x gives us negative 12x. 21 minus 9 would be plus 12. Okay, so we have a common factor of 2. We can factor that out. X squared minus 6x plus 6 over x minus 3 quantity squared. Okay, so this one is going to be difficult to factor. So the derivative will be 0 when the numerator is 0. So we can use the quadratic formula to find out where the numerator is going to be 0. So a is the number in front of x squared, which is 1. B is the number in front of x, negative 6. C is the number by itself. So we want to set this equal to 0 and solve for x. So that means that x is minus b, which is minus negative 6, plus or minus square root negative 6 squared, minus 4 times 1 times 6 over 2 times 1. Okay, so this will be 6 plus or minus square root 36 minus 24 over 2. 6 plus or minus square root of 12 over 2. 6 plus or minus square root of 4, square root of 3 over 2. So this is going to be 6 plus or minus 2 root 3 over 2. And if we divide both terms by 2, we're going to get 3 plus or minus root 3. Okay, so so those are the critical points. So get another piece of paper here. Okay, so root 3 is approximately, you use trial and error to get root 3. It's going to be approximately 1.7. So it's prime of x equals 0 when x equal 3 minus 1.7 or 3 plus 1.7, and it's going to be 0.3 or 4.7, and then we can analyze the sign. So if we just double check my work here. So we have derivative of the numerator, 4x minus 7, and minus the numerator times the derivative of the denominator, which is 1. So minus 4x plus minus 9. 12x squared, 4x squared, 12x, 19x. Okay, so okay, so if x is 0, let's do some test points. For example, if x is less than 1.3, if x is between, let's say x is equal to 3, and if x is more than 4.7, let's say x is equal to 5. Let's see what happens. We put in 0 here and we also actually, the 3 is undefined, so let's, the function itself is undefined at 3, so let's take a number between 1.3 and 3, let's say 2, and a number between 3 and 4.7, let's say 4, because the function itself is undefined when the denominator is 0. Okay, so if we put in 0 here, the derivative is going to be positive. The numerator will have will also be positive. We have 0 plus 0 plus 6, which is positive. So this will be positive. If x is 2, denominator is positive. 2 squared is 4. 4 plus 6 is 10. And this is going to be a negative 12, so this will be negative here. If x is 4, we have 16 plus 6 is 22, minus 24 is going to be negative. If x is 5, 25 plus 6 is 31, minus 30 is positive. Okay. Okay, so at this point here, we'll have a local max because it's we have a function increasing and then it's decreasing. So this is a local max, and this point here is going to be a local min, where it's decreasing, and then it's 0, slope is 0, and then it's increasing. Okay, so let's then take the second derivative, the derivative of the derivative. So f double prime, so it's going to be the derivative with respect to x of the first derivative, which is 2x squared minus 6x plus 6 over x minus 3 quantity squared. And we can use the quotient rule again. So we'll have x plus 3 to the 4th power in the bottom. And then x minus 3 to the squared times the derivative of the numerator, which will be 2x minus 6, minus the numerator, which is x squared minus 6x plus 6, times the derivative of the denominator. With the denominator, we can use the chain rule. The outer function is squaring, so it's times 2 times x minus 3 and then times 1. Derivative of the inside function is 1. And the whole thing is multiplied by 2. I have a 2 out in front here. Okay, so we have a common factor of x minus 3. So we can factor that out. This x minus 3 will cancel here. This exponent goes down 1, and this exponent goes down 1. And then we can distribute 2x times x, 2 times the whole thing. 2x times x is 2x squared. The outer product is minus 6x, the inner product is minus 6x, that gives us minus 12x. Negative 3 times negative 6 is plus 18. Distribute the 2 and distribute the minus sign, so we'll have minus 2x squared plus 12x minus 12 all over x minus 3 quantity cubed. Okay, so minus 12x plus 12x cancels. Whoops, that one there. 2x squared minus 2x squared cancels. And 18 minus 12 is 2, is 6, but then you have the 2. So it's going to be 18 minus 12 is 6, and then multiplied by 2, so you'll have 12 over x minus 3 quantity squared. Okay, so the function is undefined when x is 3. That's undefined there, and so it's not going to be an inflection point because it's not in the domain of the original function, but it could still change concavity there. So we can pick numbers on either side of 3, for example 2 and 4, and plug them in. If oh, this is cubed. If we put in 2, we're going to have a negative 1 cubed on the bottom, and that's going to be negative. If we put in 4, we'll have 4 minus 3 is 1, and we'll have a positive 1 cubed on the bottom. That'll be positive. So this, on this side it's concave down, it spills water. This side is concave up, spills water. So the concavity does change at 3, but because 3 is not in the domain, it's not considered to be an inflection point. And it's also useful to get the intercepts. So the y-intercept occurs when x is 0. So f of x, I'll write it up here, is 2x squared minus 7x plus 9 all over x minus 3. And then the y-intercept occurs when x is 0. So f of 0 is 0 minus 0 plus 9 over 0 minus 3, which would be negative 3. And the x-intercepts will occur when the numerator is 0. So you want to solve 2x squared minus 7x plus 9 equals 0. And we could try to factor this. See if it factors 2x times x will give us 2x squared. We need two numbers to multiply to 9, and the outer product plus the inner product has to give us 7. So let's say plus. It has to be a negative times a negative. So let's say minus 3 and minus 3. I think that will do it. So the outer product is minus 6x, inner product is no, that doesn't do it. So maybe we have to use a quadratic formula here. oh, no, 9. Let's try this one. Not minus 9 and minus 1. See if that works. No, it doesn't work. Let's try the quadratic formula. Okay, so A is the number in front of x squared. B is the number in front of x. C is the number by itself. And so x is going to be, oh, this didn't work, minus b, which would be 7 plus or minus square root b squared, negative 7 squared, minus 4 times 2 times 9, all over 2 times 2. So 7 plus or minus square root 49. 4 times 2 is 8, times 9 is 72. All over 4. So this is going to be a negative 7 plus or minus square root minus 23 over 4. So this is an imaginary number. Square root of negative 23 is imaginary. So there's no x-intercepts. So the y-intercept is negative 3, but there's no x-intercepts. And we could also get the asymptotes. Usually fractions will be hyperbolas, and hyperbolas have asymptotes, so we can use long division to get the asymptotes. If we divide x minus 3 into 2x squared minus 7x plus 9, 2x squared divided by x is 2x. Multiply 2x times each term. 2x times x is 2x squared. 2x times minus 3 is minus 6x. And the way you, next step is subtract, but the way you subtract algebraic expressions, you change the sign, add or subtract like terms according to the sign. So we'll have a negative 7x plus 6x is negative 1x. Bring down the 9. 2x squared minus 2x squared is 0. Minus 1x divided by x is minus 1. And then multiply. You have negative 1x plus 3. I draw the line, change the signs, add or subtract like terms according to the sign. You get remainder 6, which we can write as 6 over the divisor, which is x minus 3. So we're going to have two asymptotes. One of them is a slanted asymptote, and the other one is a vertical asymptote, x equals 3. This is slanted. And this is a vertical asymptote. So it's going to be a hyperbola. If you have a rational function that has one vertical and one other asymptote, the graph is going to be a hyperbola. Okay, so let's then sketch the graph. So I applied the y-intercept here. That's the only intercept here. And use the other one. We have the local max at approximately 1.3, and we have the vertical asymptote. This is of course undefined, and we have local minimum. These are not absolute maximums or minimum, but they're the local minimum. The asymptotes, we have the vertical asymptote x equals 3. It's a dotted line here. The slanted asymptote, it has slope 2 and y-intercept -1. So if you start at -1, that's where it crosses the y-axis. If you go up 1, you go over 1, you should go up 2. If we go over, let's say 3, you should go up 6 to get another point on the asymptote and connect the dots. And when you plot the points, then you extend it toward the asymptotes. This one has no absolute minimum. So you have a local minimum here because it's lower than anything nearby, but it's not an absolute minimum because there's lots of points down here that are smaller than the local minimum, and likewise we have a local maximum here, but it's not an absolute maximum. And that concludes this presentation.